Hello developers, in this video we're going to show you how to profile models using Qualcomm AI Engine Direct SDK. Qualcomm AI Engine Direct SDK is ideal for profiling model execution on hardware accelerators. Before we start profiling, let's walk through a few prerequisites. Set up Qualcomm AI Engine Direct SDK. Convert a model to Qualcomm AI Engine Direct model, represented in a shared object or context binary format. Prepare inputs and input list to feed to qnn-net-run. The tool we'll use to profile models is qnn-net-run. This tool expects an input list file with pre-processed inputs. Next, make sure you have a device to do the profiling and prepare a device to benchmark. Sideload Qualcomm AI Engine Direct SDK binaries like qnn-net-run or qnn-profile-viewer to the target device. Sideload all necessary Qualcomm AI Engine Direct SDK libraries. Sideload HTTP-specific libraries, for example, skeleton library. Ensure environmental paths are set including path, LD library path, and ADSP library path. If you haven't already set up the Qualcomm AI Engine Direct SDK, complete your workflow model and prepare the device to benchmark, refer to our previous videos or to the online SDK documentation and workflow. Before we start profiling models, let's do a quick review of the Qualcomm AI Engine Direct SDK workflow. Qualcomm AI Engine Direct SDK provides converter/quantization tool to convert a pre-trained model from PyTorch, ONNX, TensorFlow to an intermediate representation graph written in a high-level programming language like C++. The intermediate representation model then gets compiled with an appropriate cross-compiler toolchain to generate a shared object. Optionally, a context binary is generated from this shared object, which is compatible on all devices, irrespective of the operating system running on the device. Based on model profiling or accuracy testing, accuracy tuning or performance tuning could be done on the model. A final optimized model or context binary will be deployed on the devices. For benchmarking in Qualcomm AI Engine Direct SDK, the main tool we'll use to profile model performance is qnn-net-run. The qnn-net-run tool is a command line application written using qnn-c API. This tool will load a model shared object or a model context binary and a set of pre-processed images to perform inference. As the model gets executed, QNN will save profiling log data into a profiler log file. Commonly, this tool will take several arguments, including but not limited to the following: model, which is path to compiled model.so file, or retrieve context, which is a path to a model context binary file. Please note, model argument is mutually exclusive with retrieve context argument. Only one of these two arguments must be provided by user. Input list, which is a text file with paths to pre-processed input images. Output directory, which is a path to save output tensors after performing inference. Note, profiler log file will be written into the path provided in output directory. Backend, which is a path to backend library to execute model. This is one of the most important arguments to qnn-net-run tool. This argument specifies which backend library to be loaded and used for inference. Profiling level, which is an argument to set granularity level at which of profiling is done. Performance profile, which specifies performance profile value that may affect power versus performance trade-off. Here is an example qnn-net-run tool workflow. As you can see, a model shared object or a context binary is loaded by qnn-net-run along with an input list text file that contains paths to pre-processed image data. A command line argument is available to specify which hardware backend the user would like to execute on the model. The tool qnn-net-run will then execute the model on provided inputs on selected hardware backend one by one. After completing, qnn will write inference results, that is, output tensors, to the output directory. qnn will also write a profiling log file to the same output directory. We'll see later in this video how we can retrieve profiling log data from such profiling log files. Now let's see an example of running a model using qnn-net-run tool. In this example, we are loading a model shared object along with input list.txt file and setting the backend library to HTTP backend library. We're also setting the performance profile to burst, which will give the best performance at the cost of power. We set the output directory to write output tensors and profiling data log file with output directory argument. For profiling data, we set the profiling level argument to detailed. Please note, we can set profiling level to one of 4 available options: off, basic, detailed, and backend. The level of profiling data captured will depend on the profiling level selected. In this example, we set profiling level to detailed to get more granular profiling metrics. After executing the model, we can see that qnn-net-run tool generated the following files in the specific output directory. Output tensors for each of input images within input list text file were written to result.x directory. The qnn-net-run tool also generated the qnn-profiling data.log file. Please note, if we set profiling level to off, qnn-net-run tool wouldn't generate a profiling log file. Now that this profiling data log file is generated, we can proceed to see what data is captured by qnn and saved in this file. This qnn profiling data log file is a binary file that can only be read by a specific tool called qnn-profile-viewer. This tool is already part of qnn SDK. qnn-profile-viewer tool is a simple command line tool built on top of qnn-C API. This tool loads a profiling data log file and output profiling data in human-readable form. This binary can be run directly on target to view the profiling data. Here's the help content from the tool. It takes an input log file, which is a required argument. Optionally, output from this tool can be written to a CSV file. Output from the qnn-profile-viewer tool will contain the following matrix. init stats tells the time it took to load the model and backend library along with the dependent libraries to begin inference. Init stats shows the time it took to unload the model and destroy all contexts, free up memory, etc. Execute stats provide details on total inference time, accelerator time, and more. If detailed profiling level is selected, the profiling data will also contain layer level stats, such as number of cycles spent at each layer. Here is an example of performance metrics output by the qnn-profile-viewer tool. Let's highlight a few important details. Init stats measures the time taken to build and configure the model's execution graph. Finalize stats measures the time taken by Qualcomm AI Engine Direct to finalize the graph. Deinit stats measures the time taken to deinitialize Qualcomm AI Engine Direct graph. Total inference time measures the entire execution time of one inference pass. This includes any input and output processing, copying of data, etc. This is measured at the start and at the end of the execute call. The execution stats of each layer of the neural network model are shown here. To achieve peak throughput, Qualcomm AI Engine Direct SDK provides a tool called qnn-throughput-net-run. This tool is a multi-threaded application that can create multiple instances of the same model, running each instances within its own software thread. With multiple threads running, the application will reduce the idle time on the accelerator. This tool can also simulate concurrency scenarios when running multiple models. This tool takes a configuration.json file as an argument. More details on configuration.json file are documented in the tool section of the Qualcomm AI Engine Direct documentation. To create multiple instances, the user must use this configuration.json file to configure model instances. Here is an example of a configuration file passed to qnn Throughput-net-run tool. As part of .json file, we configure the following. The first configurable part of this configuration.json file is backends. Backends takes a list of qnn backends that a developer would like to make available for models to run. In this example, we specify HTTP as an available backend for models to execute. We must specify additional details on this backend. Details such as path to backend library, a name to refer to backend, performance profile to use, profiling level. And if employing any backend extensions, then path to qnn backend extensions library. Please note, once we declare a backend, we can refer and use this backend through backend name value specified. Next, we configure models. Models takes a list of models to load and run for a throughput exercise. Details such as model name, model path, inputs and outputs can be configured here. If a model is a shared object, we set load from cached binary to false, else true. We may provide additional details such as input or output data types, etc. Next, we configure context. Every model that gets executed via qnn gets executed within a qnn context. If we plan to run more than one instance of a model, we may need to create multiple contexts so each instance can run in its own context. Hence, context takes a list of qnn contexts. Finally, we configure our test case. In each test case, we configure how we want to run the models on available backends. The main detail here is the configurable file threads. As explained earlier, each model instance will run in a separate thread, so we must configure each thread on how we want to execute them. Also note, we bind the model to a context and a backend in each thread and give it a name. It is important to configure all fields correctly. For more details on this configuration, please refer to following documentation. Here is an example of executing a model using qnn Throughput-net-run tool. Here, only one instance of the model gets executed within its own thread. In this example, HTTP thread 1 graph execute gives stats on average inference time, and HTTP thread 1 thread execute gives stats on total time to completion of execution. Another example we see here is executing two instances of the same model using qnn Throughput-net-run tool. Here, we spin two instances of the model getting executed within their own threads. In this example, HTTP thread 1 graph execute gives stats on average inference time for instance 1, and HTTP thread 2 graph execute gives stats for instance 2. HTTP thread 1 thread execute and HTTP thread 2 thread execute give stats on total time to completion of execution for overall thread completion. So far, we looked at how we can check performance of models in Qualcomm AI Engine Direct SDK and its tools. Now let's look at one more feature that Qualcomm AI Engine Direct SDK provides: Linting profiling mode. Linting profiling mode provides more granular profiling data for models running on HTTP. In previous profiling levels, we know relatively how much time or number of cycles spent at each operator within a network. It doesn't provide information on any op parallelization details. As HTTP can execute operators in parallel using HVX, HMX intrinsics, it makes more sense to check if there are any ways that we can further optimize the parallelization of operator execution. Linting profiling mode gives us insights into such profiling data, so we can understand how HTTP schedules operators within the model, and possible ways to optimize if there are any bottlenecks. Here are a few details about linting profiling mode in QNN. Reports generated have per-op profiling results in cycle spent instead of time in microseconds. There is no direct conversion methods from cycles to microseconds. So we'll use relative number of cycles spent at op for comparison. A Chrome trace can be exported from linting profiling data for visualization. Linting profiling report provides the following entries per op. Cycles, the number of cycles spent executing the operator on the main thread. Wait, the wait entry reports the number of cycles spent waiting before op execution on main thread begins. This wait period can be attributed to various factors, such as scheduling or waiting for some background HVX or DMA activity to finish. Overlap. The overlap entry denotes the number of cycles spent on at least one background op while this op is executing on the main thread. Overlap wait. The overlap wait entry denotes the cycle spent on at least one background op while the main thread was waiting. Resources. The resources entry lists the different resources used by the given op, namely some combination of HVX, HMX, and DMA. Here is an example of how one can invoke the linting profiling mode in Qualcomm AI Engine Direct SDK. As discussed previously, we'll use qnn-net-run tool to profile model execution. To get linting profiling data, we'll use the backend extension features in QNN. Backend extensions can be supplied to qnn-net-run tool via a couple of JSON files. We can add linting profile mode for profiling level in one of these configuration JSON files. Arguments to qnn-net-run tool here are model, path to the model file. Here we are using a compiled QNN model. Backend, path to the qnn-HTP library. Input list, path to list of inputs we would like to use for this profiling run. Profiling level, it is important to set profiling level to backend here, as we plan to use backend extensions to set linting profile. Config file, path to backend extension JSON file. This JSON contains path to backend extensions library and actual backend extension configurations. Output directory, path to output directory where profiling data will be written. Once qnn-net-run tool completes its run, QNN will write a profiling log data to output directory. Pull or copy this log file back to a host machine. We can then use qnn-profile-viewer tool to generate human-readable profiling data, which will contain linting profiling metrics we just discussed. Note that qnn-profile-viewer tool takes an additional argument, reader. To generate human-readable profiling data, we set this reader parameter to lib qnn-HTP-profiling-reader.so library. Here is an example of how that generated profiling data would look like. As mentioned earlier, it provides insights into numbers of cycles spent at a particular op, wait, overlap times with other background ops, and resources used to execute op. We'll see an example of how we can use this linting profiling matrix to optimize a model later on in this video. We just saw how to generate a human-readable profiling data. To generate Chrome trace, we just need to set reader parameter to lib qnn Chrome trace profiling reader.so instead of lib qnn HTP profiling reader.so. This will generate a Chrome trace JSON that we can load using a Chromium browser. For loading a Chrome trace JSON file into a Chromium browser, visit one of these websites. Here is an example of what Chrome trace will look like in a Chromium browser. Chrome trace shows both foreground and background op executions. For each op, we should ideally have a good overlap indicating parallelization. So far, we saw how to use a linting profiling model to generate op-level profiling metrics, including foreground and background operator executions. Now, let's use in linting mode to see if we can optimize a model by looking at an example. In this example, we have a very shallow neural network model in ONNX format. This model has two intermediate branches, each branch performing a couple of convolutions before their results are used in a sub-operator. We will show how this sub-operator would be a bottleneck when executing this model on HTP using linting profiling mode. To begin, we'll follow a typical Qualcomm AI Engine Direct SDK workflow. First, we'll convert, quantize, and compile models, or generate context binaries. Next, we'll execute the generated model.so, or context binaries, on HTP using qnn-net-run tool on a set of inputs with linting profiling mode enabled. Finally, once qnn-net-run completes and profiling data log file is written to output directory, we'll copy the log file back to host machine and using qnn-profile-viewer tool to generate human-readable profile data or a Chrome trace JSON file to visualize model execution. Here is an excerpt of what qnn-profile-viewer tool returns after parsing qnn profiling data log file, specifically for sub-operator. You can parse through this profiling data of each op to see number of cycles spent, weight, and overlap times for the op. For the sub-operator, we will see that overlap time is not significant compared to the total time spent at the layer. Let's look at the same data, but from a Chrome trace. In Chrome trace, we can see that sub-operator and background op doesn't have much overlap. Sub-operator takes significantly longer. Given the op parallelization is not significant, we can categorize sub-op execution as a bottleneck. Let's see how we can optimize this model to see if we can improve performance of the model. Clearly, sub-operator is inefficient as it predominantly runs on HTP using HVX resource. To remove this bottleneck, we apply two optimizations. Optimization number one, instead of two branches, each performing a couple of convolutions, let's merge the two branches into a single branch. This can be done by modifying the convolution operations. Optimization 2, after merging two branches, there is no need for a sub-operator. We replace this sub-operator with another convolution operator to yield an equivalent model. After applying the two optimizations, we profile the model again. Note, if we change the architecture, the model may need some retraining. Once again, we go through the typical profiling workflow. We convert, quantize, compile, and execute the model on HTTP. We then use qnn-profile-viewer tool to generate human-readable linting profile data, or Chrome trace JSON for visualization. With the updated model, we can clearly see that there is better parallelization. That is, both foreground and background op execution has relatively significant overlap. Looking at profiling data, we can observe that model can run faster now compared to previous version of model. Thus, we can conclude that we have removed the previous bottleneck with the help of linting profile data. So far, we looked at ways to profile models. Here are some factors that might affect the performance of a model and guidelines to keep in mind when designing and executing a model. For a Conv2D operator, it is recommended to keep depth of hidden convolution or activation layers to a multiple of 32. Use Performance Profile API to check power versus performance trade-off. Burst mode gives best performance as the clocks are volted to Turbo L1 mode. Using detailed or linting profiling modes may impact performance of operator or model as more detailed diagnostic data is collected. Utilize heterogeneous computing by executing workloads on different backends like GPU and/or HTTP. we have learned how to profile models in Qualcomm AI Engine Direct SDK. For additional details, please review the Qualcomm AI Engine Direct documentation to learn more. Thanks for watching.